Hello, advanced algebra students. I'm really happy to be teaching you another lesson. Today's lesson is going to be on solving equations. Now, obviously, all of you have learned how to solve an equation before, but what we're going to do today is talk about some common scenarios that can come up when you're solving equations and how to handle those scenarios. So, for example, what do you do when an equation has a parentheses, fraction, decimal, or how do you handle potential word problems that might come up? So all that you need to take your notes today is a piece of paper and a pencil. And we will go ahead and get started. Let's start off with a fairly basic example. We're going to do, for example 1, 5d plus 17 is equal to 4 times the quantity d plus 3. In this kind of a situation, it's important when we have the parentheses that we distribute, and then if we have any like terms, that we combine those like terms. So we want to move our x, or in this case d, to one side first by subtracting 4d. And then we're going to have d plus 17 equals 12. And then when we subtract, we get d is negative 5. So that's a pretty straightforward problem. Now, there are some other scenarios that can also come up when you are doing an equation with a parentheses. And normally I try to streamline the videos for online learning and not include too many examples, but there are some other scenarios that can come up, and I do want to make sure that we cover each type of possibility. So let's look at the equation 4x plus 6 equals 2 times the quantity 2x plus 3. We do want to distribute like we just said. When we do, we get 4x plus 6 equals 4x plus 6. Now that looks a little bit weird. When you try to get the x on one side, that's okay, you can do that. Then you end up with something really strange looking, just 6 equals 6. Does anybody know what that means? What does it mean to say 6 equals 6? What am I saying there? I haven't actually solved for x. What it means is that because we get a statement that's always true, this is something called an identity, because 6 is equal to 6. And what it means is that there is an infinite number of solutions. Infinite number of solutions. So in other words, whatever number you plug in for x, you are going to get a true statement out. So this can work with anything. So the first example, we had an actual number, d equals negative 5. In the second example, our answer was just infinite number of solutions. Now let's do a third potential kind of answer that we could get. If we look at example 3, let's do 6x minus 5 equals 2 times the quantity 3x plus 4. All right, the first thing we would want to do, obviously, is distribute the 2 and get 6x plus 8 on the right. This time, when we subtract 6x from each side, we get a statement that is not true. We get that negative 5 equals 8, which we know isn't true. So does that mean, what happened here? Did I make a mistake? Did I do something wrong? This isn't true. So what does that mean? What it means is this is an impossible situation, and that no matter what we try to do for x, nothing's going to work. So in this case, because we get a statement that's never true, our answer is just going to be no solution. So the answer is that there is no solution. All right. Now, a big thing that's going to come up in this class and all of your future math classes is working with equations that have fractions in them. So I like to break this up into two categories. One category is if the equation has one fraction, and another category is if the equation has more than one fraction. So let's talk first about what to do if an equation has one fraction in it. So for example number 4, let's say that we have 2/3 times the quantity x minus 2 equals 18. The simplest way to get rid of a fraction when there's just one of them in the equation is to do something called multiply by the Can anyone guess? Multiply by the what? Multiply by the reciprocal. So reciprocal means you're taking the number and flipping it upside down. So instead of having 2 over 3, we're going to have 3 over 2. Now, the cool thing about doing this is that on the left, the 3's cancel out and the 2's cancel out. On the right, we can cross cancel 18 divided by 2 and get 9. Some of you are saying, wait a minute, hold on, what did she just do there? I don't like that. This is something that's going to come up a lot in advanced algebra. It is true when you're taking 18 times 3 halves, you can multiply across the top and the bottom and then cancel. So you can take 18 times 3. I don't know what 18 times 3 is. I could probably do it in my head if I worked hard enough. But I'd rather do 9 times 3. So I just said, okay, here, 18 divided by 2 is 9. So I can replace that with a 9. And we can talk about that more during the Zoom if you have a question about it. So now that we've multiplied by the reciprocal, we have a really easy problem left. It's just x minus 2 equals 27. Isn't that nice? So we just wiped out the fraction and made the number smaller. Everything's looking good. Then we just add 2 to both sides and we get that x is 29. So that is a very straightforward way to handle an equation when there's just one fraction. Now, another thing that comes up, obviously, is that you have more than one fraction. So let's talk about, for example, 5, what to do when you have more than one fraction. The example here I have is 1/2 x plus 1/3 x equals 2. The strategy that I would recommend you using when you have an equation with more than one fraction is to multiply by, does anyone want to guess? What could wipe out all of my fractions? Multiply by the lowest common denominator. So, if we look at 2 and 3, the lowest common denominator is 6. So I want to multiply everything I see by 6, can't play favorites. Here, the 6 divided by 2 becomes a 3. Here, the 6 divided by 3 becomes a 2. So now we have this really complicated looking equation that turns into a very basic equation. It is just 3x plus 2x equals 12. Isn't that great? Then when we combine like terms, we get 5x equals 12. And then we divide by 5, we get x equals 12 over 5. Okay, so we've talked about what to do when you have parentheses, what to do when you have one fraction, what to do when you have more than one fraction. Let's talk about a strategy that you can use when you have decimals and you're solving an equation. So we'll make this example number 6. Let's work with the equation 0.2 plus 0.4x equals 0.8. Can anyone figure out what I would need to multiply by to make all my decimals go away? How could I move everything over one spot to the right? The answer is that I would need to multiply everything by 10. Now, if the decimals went out 2 spots, I could multiply everything by 100. But in this case, 10 works great. And now I just have 2 plus 4x equals 8. I can subtract 2 to get 4x equals 6. Then I can divide by 4, and x equals 6/4, or when I reduce it, 3/2. Okay, so that covers kind of your basic kinds of equations. Now, I do want to talk about word problems. The book that we are working out of this year, I have to be honest with you, I really do like it. And I know this might sound kind of strange, but part of the reason I like it is because I think it helps students to learn to reason, justify, and explain even better than in our previous textbook. I think it really does prepare you for more difficult standardized test questions, say on the SAT, or more difficult questions in future math classes. So the word problems in this book, they do have usually several on every assignment, and some of them are fairly difficult. So I'd like to give you some steps that I recommend you follow when you have an equation with a word problem in it. So the first step is going to be to determine what your variable is. Determine what variable is. Now, some students resist this, but I really do recommend you write down x equals and identify what it is at the beginning of the problem. It will ensure that you're setting up an equation that will actually answer the question. Now, my number one tip for solving word problems is when you are determining what the variable is, read the last sentence. 99% of the time, or maybe 90% of the time, when you're solving a word problem, the last sentence of the word problem will tell you what your variable should be. Step 2, after you've done that, is to set up your equation and solve it. So set up equation and solve. And then step 3 is to check your answer. You can always plug your answer back into the word problem and make sure that it does work. Now, I'm going to jump right to the last example here because, again, I'm trying to streamline things. If we were doing this in class, we would be doing more examples. But I'm going to give you an example that is very similar to one of your homework problems, and I think it can be pretty darn difficult if you haven't seen it before. So I'm going to read it slowly. Please don't feel like you need to write it down. I'll write down everything you need on the board. So as long as you're writing on your paper what I'm writing on the board, you should be good. So here's the problem. And don't get overwhelmed. Remember, we're going to read the last sentence and deal with it then. A bee flies at 20 feet per second directly to a flower bed from its hive. The bee stays at the flower bed for 15 minutes, then flies directly back to the hive at 12 feet per second. It is away from the hive for a total of 20 minutes. How far is the flower bed from the hive? Now, this is a really complicated problem. I had to tell you kind of a funny story. When I first got this textbook last year, I asked a substitute teacher that was helping me at the time to do some of the keys for me on my homework. And when she got to this problem, she's a really, I won't list names or anything, but she's a great teacher. She's been teaching math for a long time, and she said to me that she found this problem difficult. And I do too, so it wasn't just me. But so if this seems like a difficult problem to you, that's because it is. But that's all the more reason for us to use the methodical steps that I just listed. So we're going to read the last sentence. The last sentence says, how far is the flower bed from the hive? So I'm going to set up a variable here. Let's call it D. And I'm going to have D be distance from the hive. Because the question was, how far is the flower bed from the hive? So that's what I'm trying to find out. What's the distance? So I'm going to write that down. D equals distance from hive. Now, another thing about this problem is I'm noticing that there's times, distances, and speeds in here. And so that is telling me kind of like as a big clue that I need to know the formula that I learned in Algebra 1, that distance is equal to rate times time. This does come up in the word problem several times in the first chapter of the Algebra 1 book that we're working out of right now. The formula distance equals rate times time. The trick in this problem is to reconfigure this formula by dividing both sides by r. When you do, you get a different version of the formula. They are equivalent. But distance equals rate times time is how we often use the formula. It is equivalent to say that time equals distance over rate. Now, when you are dealing with very complicated problems, I have found it extremely important to put down what you're trying to do in words first and then build your equation off of that. So I know that I read the problem kind of quickly, and I apologize that we're not, in an in-class learning environment. But like I said, I'm trying to streamline things, and the notes that I'm reading for, we're only doing bits and pieces of, and it wouldn't really make sense to give this to you. So we're talking about time in this whole problem. So what I'm going to do is I want to say that the total time is equal to the time that the bee took to get to the flower bed plus the amount of time the bee was at the flower bed, plus the time to get back to the hive. And I'm going to go ahead and read the problem one more time for some of you that might be frustrated thinking, man, that just went too fast. But now that you have this written down, I think you can see where we're going to go with this. A bee flies at 20 feet per second directly to a flower bed from its hive. So that's the first part of this, the time it took that bee to get to the flower bed. The bee stays at the flower bed for 15 minutes. That'll be this part here, how long the bee was at the bed. Then flies directly back to the hive at 12 feet per second. That's the time back to the hive. It is away from the hive for a total of 20 minutes. How far is the flower bed from the hive? Now, something that you may have noticed is that there are different units in this problem, so that also kind of makes it difficult. Notice that the units are in seconds and minutes, and so we need to be consistent, and generally, so that we don't have to work with fractions, it will be easier to turn everything into seconds. So for example, we need to figure out how much 15 minutes would be in seconds, because it says that the bee stayed at the flower bed for 15 minutes. Well, each minute has 16 seconds in it, so that would be 15 times 60. Did I say 60 or 16? It has 60 seconds. That would be 15 times 60 seconds, or 900 seconds. So on my equation where it says time at the bed, I'm going to put 900 because the bee was at the flower bed for 900 seconds. Now, it says that the total time that the bee was away from the hive was for 20 minutes. So we need to figure out what 20 minutes is in seconds. If we take 20 minutes and turn it into seconds, we would need to take 20 times 60 to get a total of 1,200 seconds. So the total time that the bee was away was 1,200. You can see how we're starting to fill stuff in here. This is a hard problem, so if you're thinking, oh man, I'm never going to be able to do this, just know that this is hard. So it's not you that's the problem here. All right, now, how much time did the bee take to go to the bed? Well, we know that time is distance over rate. And so, let's see here. It says, we don't know what the distance is, so we're going to leave that one blank. But we know the rate was 20 feet per second. So since time is distance over rate, and we're trying to represent the time to the bed, we're going to put d, which is our distance that we don't know, over the rate that they just gave us, which was 20. Now it says when the bee flies back to the bed, the bee flies back at 12 feet per second. So again, when I'm trying to represent the time to the hive, I need to write distance over rate. So I'm going to write d since I don't know what the distance is, but the rate that time is just 12 feet per second. Maybe because the bee is loaded down with the pollen now. I don't know. All right, so now we've got an equation. Now the cool thing about this problem is not only does it demonstrate how to set up an equation for a complicated word problem, but it also helps us review what we just talked about in terms of equation solving strategies. So I would like you to ask yourself, this is the equation here. How many fractions are in this equation? Is there one fraction or more than one fraction? Given that there's more than one fraction, what did we say earlier in the notes would be the most efficient way to solve this equation? The most efficient way when we have more than one equation is to multiply by the lowest common denominator. So we need to think of the smallest number that 20 and 12 both go into. Do you know what that would be? The smallest number that 20 and 12 both go into is 60. So what that means is to make this equation more manageable, I want to take everything in my equation and multiply it by 60. I can't play favorites, so I have to multiply everything by 60. Now, when I do that, on the left, 60 times 1,200 is 7,200. Here I can cross cancel. 60 divided by 20 is 3. This becomes 3D. See how much nicer this is? Then when I take 60 times 900, I get 5,400. And again, the 60 and the 12 will cancel here to make a 5, so this just becomes 5D. Awesome. We're coming into the home stretch here, and after this we'll be done. Now we want to combine like terms, like we talked about earlier. So 3D plus 5D is going to be 8D. And of course, now we want to use our opposite operations. So we're going to subtract 54,000 from both sides. And I'm going to get that 8D is equal to 18,000. And then the last step is to multiply by 8. And D is going to be 2,250 feet. Now, some of you might be thinking, gee, that example is just way too much work. It is a lot of work, but I did want to let you know part of the reason I did this is A, it's in the homework, and B, I've seen several examples like this throughout the book. So this isn't the only time you're going to see this very similar kind of problem. So I would recommend, if you need to, obviously rewind the video so that you can listen to maybe steps of solving that more than one time, or pause the video so that you can stop and make sure that everything is written down correctly. But anyway, I can't wait to see you in Zoom. I hope you're having a good day. All right, bye.